All right, well, welcome back everybody to track 2, Making Tectonics. I'm excited to introduce our 3 panelists leading the discussion today. First, we have Dr. Weichiang Peng, who's an associate professor of civil engineering, professor of intelligent infrastructure at Clemson University in the Glenn Department of Civil Engineering and a member of the Wood Utilization plus Design Institute. Dr. Peng received his master's and PhD in civil engineering from Michigan Tech and held his postdoctoral work at Texas A&M University. Current areas of focus and ongoing research projects address structural reliability, performance-based engineering, and performance of low and mid-rise wood structures subject to natural hazards. Welcome. Next, we have Dr. Greg Kingsley, is a licensed engineer in countless states and the president of CEO of KLA Engineers and Builders operating out of Colorado. Dr. Kingsley attended CU Boulder, UC San Diego, and the University of Pavia in Italy before forming KLA and Engineers and Builders. The work has evolved from early investigations of structural masonry and unreinforced masonry into innovative wood structures addressing carbon sequestration and environmental responsibility. Most notably, his work with Shigeru Ban Architects on the Aspen Art Museum. Welcome, Greg. And last but not least, we have Lucas Epp, who's a structural engineer with at least 15 years of experience working in North America, UK, and New Zealand for Bureau Happold and currently with StructureCraft. With guest lectures at ETH in Zurich and the Architectural Association in London and projects ranging from the Olympic Stadium in London, a 300-meter tower in Kuwait, and the 200-meter arena stage theater facade in Washington, D.C., it is clear Lucas is making a significant impact on the advancement of wood architecture and engineering. A short prompt for the panel, the American architect Louis Kahn taught us to ask material what it wants to be with the intent to discover the range of forms it is willing to accomplish. Certainly, to bend the will of material would be to break its spirit. However, not to ask it any questions at all is to strip it of a voice. If tectonics is the marriage of science and art through construction, contemporary solid wood building tectonics have addressed only half of this marriage, science. Investigations of cross-laminated timber tectonics have in large part been asked to only solve the mathematical questions of structural loads resulting in clunky forms and inane connections to no fault of the engineers. To use the words of Deleuze and Guattari, it is a question of surrendering to the wood, then following where it leads by connecting operations to a materiality instead of imposing a form upon matter. I'll leave it with that and go ahead, Dr. Peng.
Thank you. I'm going to go ahead and share my screen. All right, tell me if you can see the full screen right now.
Yep, looks great.
All right, thank you. So I'm, as mentioned, my name is Weichiang Peng. I go by Peng. I'm a professor of intelligent infrastructure at Glenn Department of Civil Engineering. So I picked this topic here. The title, could cross-laminated timber be a solution to both climate change issue and also resilient housing needs here? So if you look at today's, roughly about like 50% of all the world population kind of live in some sort of urban or city environment or near city. And it is projected that by 2040, this number will increase to about 75%. There's been more population will be concentrated in highly populated city area here. So most of the building, right, in our city, they are built usually using steel or reinforced concrete, rightfully so, because of the needs for more dense housing. If you look at the global CO2 emission by sector, this bar chart kind of tells us that the building material and construction account for 11% of the CO2 emission. With the housing needs, this means we need to build more housing and the climate change issue. So how could we kind of solve this conflicting kind of interests here, competing factor? So if you look at concrete, if we somehow replace the use of concrete, 1 meter cube of concrete replaced by timber or wood, we can actually reduce the emission of CO2 by 1 ton. That means we're going to cut down the 11% CO2 emission from the construction industry here. So, we've been kind of using the power of sun, right? Grow our fruit. Maybe we could also grow our city using the same, kind of power of sun. It's been grow our city by using more wood instead of using steel and concrete. And in terms of United States, what we know here is about 40% of the US population actually reside near the coastal area county. Many of us, we like to live close by to waterfront, and more population, in fact, in US will kind of shift towards like coastal area. One thing about coastal area here is it is also subjected to many natural disasters, especially like hurricane is subjected to high wind, especially along the coastline, eastern coastline and Gulf Coast area here. And we often see, after like major hurricane make landfall or even tornado event, all our structure are damaged, especially like residential home or apartment building here, hotel and so on. If you look at the in terms of economic losses on average, hurricane and also windstorm, thunderstorm, tornado related event, actually this number, including flooding as well, account for about 54 billion US dollar. And if you break it down further, like 34 billion is like how residential, home dwelling, and 9 billion lost to commercial, and 12 billion to kind of public sector building, right? So we all kind of, many of you, I believe, understand like cross-laminated timber is kind of much better or resilient structure. So we suspect, it has the potential to resist the demand of high wind event. So in Clemson, we kind of look into this problem here. So I'm a civil engineer and professor by training. So we have a several project looking into the potential use of CLT for high wind application, all right? So I'm going to go through some of the research study. So one here is, at what kind of debris impact resistance we can expect from CLT. Obviously, in high wind kind of situation, you have debris flying around. It might impact the building envelope of our structure. So regular light frame structure, it is not very resistant to debris impact. We also have some research conducted looking into the lateral load impact on the building. It's been the wind blowing on the surface of our building. At the end, we kind of quantify overall as a building performance compared to light frame current construction versus CLT, what kind of added benefit we can get from CLT. And at the end, I'm kind of trying to answer this question. Is it worth it building residential structure with CLT in terms of the risk and also economic assessment risk? That means if it's safer, significantly much safer than light frame. Economic, that means how much it's going to cost. Can we reduce the kind of future potential damage due to natural disaster and then somehow break even with the cost, right? I have partial answer. I don't think I have the complete answer here. So in terms of debris impact, at Clemson, we conducted some debris impact tests. So what you are seeing here on the screen here, the right-hand side is actually the picture showing a debris cannon. It is not very sophisticated piece of equipment. Basically, it's just a tank. We put in pressurized air and we put 2x4 into the tube here, and we release the pressure quickly and shoot the 2x4 at different debris travel speed, missile speed here to simulate the possible missile or debris we observe during high wind event, tornado or hurricane here. All right. So we tested a total of 14 panel, different missile mass and speed and the impact location. If you hit it near the corner versus near the middle of the panel, you give you different response. And some location is much more vulnerable. And also the connection orientation. Sometimes you have the panel directly bearing on a return wall. Sometimes it is not, when you hit it on from the other angle here. So here I'm showing one of the high-speed video camera footage. This is a 15-pound 2x4 at 102 miles per hour here. So we vary the debris mass and also the debris speed here by adjusting the pressure of our air cannon. As you can see, in this case, the CLT panel, imagine this is your wall panel, actually able to stop 15-pound 2x4 at 100 miles per hour wind speed here. Debris speed, not wind speed. This is actually very high debris speed here. If we tested some light frame, for light frame, the 2x4 pretty much just punch through, like cutting through a piece of paper. So, if you follow the ICC 500, the FEMA kind of safe home guideline, we need to define certain failure criteria. So there are 3 different failure criteria. Obviously, if you have the debris punch through, like penetrations, that is considered failure. If you have permanent deflection, if you look at the picture in the middle here, you have some deformation at the back side of the panel. Anything that kind of more than 3 inches is considered failure here. The other failure definition here is if you somehow have part of the wall dislodged, for example, one piece of the lumber delaminated from behind the wall, that is considered failure as well. So we track all those, at different impact location, corner, middle, and so on. So at the end, I'm not showing the detail behind the scene. So we tested different location and different panel. We come up with, this is called the fragility curve. What you are looking at here, the vertical axis tell you the probability of failure. When I say failure, that means the 3 failure criteria I mentioned before here. Horizontal axis tells us the intensity measure. It is the wind speed, the debris speed, travel speed. And we have 3 different curves here for different debris mass, how heavy is the mass. The black color curve here is for 6.5 kg. And then the blue color dashed line is for a much lighter debris here. So in general, if you want to take away here, is under EF2 kind of condition here, a three-ply CLT could stop almost all the EF2 or below debris with only very low probability of failure or punch through. If you look at the most severe tornado, EF5, right? So there's a kind of 50-50 chance we can stop the debris. Remember that EF5 is pretty intense tornado event here, right? So that is the basic kind of overall debris impact resistance of CLT here. We also look at what happened when the building actually under lateral load, this means the wind pressure on the surface of the structure here. Okay. So this video footage here kind of shows a test we conducted in our lab. So in this test, we tested a wall with something called a return wall. You see here there's a wall perpendicular to the in-plane wall at both sides. At some location of the structure, you're going to have return wall connecting to the in-plane wall. The top CLT, it is to represent the floor diaphragm or the roof diaphragm. So what we observe is we measure the force at the actuator and also the displacement response, and we also keep track of the separation between all these panels here, the bracket, the hold down devices at the end. Right? You can kind of see the panel uplifted. You can see the separation. Right? And I'm going to skip to the next kind of video. So for the next kind of test, we also perform similar tests. However, in this case, it is a test without the return wall. The spin is simply an in-plane wall here. In fact, right now, most of the design assumption, engineer, if they perform the calculation, design the structure, we typically ignore the contribution of the return wall here. So we also kind of tested this kind of situation, right? And I think I'm going to kind of quickly skip to it to the end of the video. In here, we could see much more kind of separation and damage without the return wall. This is kind of at the end of the test, you can see the separation. What we observe here is with the return wall, actually it provides much more stiffness and also the anchorage behavior. So if you look at the result, here the results show the blue color curve, show the peak load, the test without return wall. the red color kind of envelope curve kind of show the test with return wall. In fact, we see a significant increase in the load carrying capacity and also ductility. That means how much displacement it can deform before it kind of completely loses its capacity. So in the future, I think especially for CLT, this kind of structure, we should consider the composite action and provide information to engineer how to design for the composite action. So, as part of our kind of study at Clemson, we also perform connection tests. Obviously, the CLT structure, most of the damage happen around the connector. The panel itself usually stay pretty rigid. All the deformation and damage happen at the connector. So we test all this is because we cannot keep testing all those full-scale wall in our lab. It's pretty time-consuming and cost a lot to kind of conduct the test here. So after we perform all the connection tests, what we could do here is build computer model and put in all the behavior of the connector. The connector is much easier for us to test in a small scale. And we create the computer model that can actually mimic our full-scale test response. And from there, we can kind of put together a full-scale CLT building and then use computer to simulate the behavior under different wind load and debris impact, right? So at the end, we consider like the moment, rotation, the connection failure, and so on at different panel joint. So collectively at the end, we are able to kind of quantify, hey, for a typical residential building, if we have light frame, we have a lot of experience with light frame versus CLT, what kind of performance increase we can obtain here. So again, this is something called a fragility curve. Vertical axis tell you the probability of failure, damage to the building, light frame versus CLT. Horizontal axis show us the wind speed, estimated tornado wind speed here. Clearly you could see like CLT is much more beneficial here. It can pretty much kind of, resist damage up to EF3 tornado. Around EF4 and 5, you start to see a high probability of failure. Consider light frame structure, pretty much under EF1 and above, you can expect almost total destruction to the light frame building here. So clearly we see benefit in terms of, building using CLT here. I talk a lot regarding residential low-rise structure. In fact, the major market right now for CLT is in like mid-rise and also tall CLT building here. What you are looking at here is the broad common, a tall wood house, student housing, a student dorm constructed in the UBC campus in Canada. This is an 18-story CLT building. They have a concrete core to support the building. And in this kind of building, often you see like big opening at the perimeter of the structure. That means there's not much wall to provide shear resistance, okay? So if you look at the floor here, just take this piece of floor, it's called a kind of CLT floor diaphragm. That's why we quantify it as a cantilever diaphragm, because why? It's kind of attached back to the core structure here, right? So it's kind of fixed to the concrete core. If under kind of wind or earthquake kind of loading, push on it, we can expect kind of shear deformation. The floor will try to deform into parallelogram here. So far, there's not many kind of tests for CLT diaphragm. So what we did here at Clemson, we constructed a full-scale CLT diaphragm, a 20 feet by 20 feet CLT diaphragm, and simulate the cantilever behavior. What you are looking at here at the corner, the steel beam, it is to simulate the concrete core, fixed condition, and we use actuator to push the end. In this diaphragm, we have 8 pieces of 5 feet by 8 feet CLT panel. At the joint here, we routed a groove of 1 inch deep and then put plywood on top and then use nail to stitch those joints together. At critical location, we also put in tension strap to carry the tension load here. If you push on it at the end of the cantilever diaphragm, here, right, at this joint, it will try to open up. So there's a very high tension force. So we use like tension strap to kind of pull it together. Now, so and based on our engineering knowledge and all, we designed this diaphragm. You can take up to like 22 kips of force from the actuator. So this is a picture kind of showing the actual diaphragm in our lab setup. You can see the metal strap here and the giant hold down manufactured by Simpson company, Simpson Strong Tie company. So here I'm just kind of showing a video. We put a GoPro in our lab at the roof of our lab here, looking down to the diaphragm. What you see is the actuator keep pushing on the diaphragm, and you can kind of see the metal here shining, right? Kind of shine up here, shiny, kind of light reflection. That is actually the metal strap buckle is almost break here. And we keep pushing it, at some point it's kind of break. You can see the separation here. So we are able to quantify at what point the strap will break and at what load here. So at the end, if you look at the result, briefly look at the summary, we look at the peak loads is about more than 42 kips, slightly over 42 kips at around 4 inches of displacement. In terms of the engineering calculation, in fact, it's not that, it's quite accurate. If the engineer go to the engineering principle, our design load is 22 kips. We actually have a safety of margin of about 1.8, close to 2, which is what we target. And also the tension strap matter that did not break until post-peak. This means before the design load, it actually is protecting the diaphragm without breakage. So that is what we learned. And we also similarly, we put together a computer program to kind of model the whole thing by simply testing all the connection. We are able to use computer program to represent what happened in the full scale. And again, it is too time consuming and too costly to keep testing every possible configuration. So what we can do here is using computer program to test different configuration and layout for CLT diaphragm. Now, with that, I'm going to come back to try to answer the question: is it worth it building residential structure with CLT? In terms of risk assessment, it's been the safety. So what you are looking at here is 2 maps. The one to the left show something called the reliability index. The higher the number, right, the beta reliability index, that means the safer the structure under tornado. The right-hand side show the CLT construction. You can clearly see that for CLT construction in majority of the US is actually pretty safe. Anything that is kind of more than 4, the reliability index, this means it's pretty safe here. If you look at light frame construction, you have a lot of location where the reliability index is clearly below 3.5, 3, or even 2 here. This means it's very high risk to damage, all right? Now, so we know that it's pretty safe using CLT compared to light frame. How about cost? Is it worth it? So we actually cost out, let's say, a typical light frame structure at a certain location. In here, we're trying to compare the same construction by break down the whole construction cost into project preparation, foundation, and so on. CLT at the end costs more because it's used more wood, the material wise and so on, compared to light frame, 393,000 versus about 476,000. Now, we also went through the cost benefit study, assuming a 50-year lifespan for the structure here, and look at different locations. Let's say Huntsville, Alabama, much higher tornado risk. Greenville, South Carolina, kind of moderate, and then Denver, Colorado, it's pretty low tornado risk here. And we quantify the possible damage throughout the 50 years based on what we know the hazard, right? And then these are the expected loss cost average. Obviously, if you get direct hit by EF5 tornado, you're going to cause more damage. If you just hit by EF1 or 2 throughout the lifetime, it costs less. This is the average value. At the end, we compare light frame to CLT. Well, for the, we turn all this value into net present value here. Clearly, we're not able to cut break even. So the CLT still costs more, like 453,000 versus 390,000 for Huntsville, Alabama. For other location, Denver, still we don't see the break even at the highest hazard location in Huntsville, Alabama. So at the end, I think, is it worth it? If you just look at direct economic losses, I would say not worth it. However, one thing you need to recognize here is we have not considered other costs such as loss of human life, and then the downtime, so injury to the occupant. These are the costs we have not included. If you include those kind of costs, perhaps it is worth the investment to build even residential structure using CLT here. I think that's all I have to kind of share with you guys. I'm going to pass my presentation. I'm going to stop sharing my screen and then pass it to Greg next.
So that was a really good transition, I think, to my presentation, which is about structural and cost optimization of mass timber building systems. I'm going to dig into a little bit the very last thing that Peng was talking about, and hopefully offer some hope there before the end of it. So really, this presentation for me was born out of frustration of working with developers and architects, owners, engineers, all that are really interested, like the people at this conference, to build mass timber structures, and then running up into the wall where you get your first price estimate or cost estimate, and they say, well, this mass timber stuff is way too expensive. So it goes off the table, and that's the end of that. And I wondered what I could actually do to absolutely to maximize the possibility of success with a mass timber building. Yesterday, there was a bunch of questions that were asked that kind of were framed in the form of, well, we're designers. What can a designer do? What can a designer leverage? And that's really what this is about. It's about really decisions that designers make that ultimately can really affect the cost of the building. Drew yesterday from Structured Craft talked about this at some length as well. In fact, if you've been listening closely, I don't think there's anything that is in this presentation that is different from what you may have already heard at some point in the symposium, but it'll just be presented maybe in a little bit different way. My approach is to go through the dollar cost of different parts of a mass timber building, starting at the low end with elements, and then working my way up to just single bays, and then larger building types where we actually incorporate all the IBC building types, and then looking at entire building archetypes in steel, timber, and concrete. And I'll finish with a little bit of discussion about embodied carbon, because I've vowed not to talk to groups of people without bringing it up ever. So I'll finish with a hopeful note there. So let's start with just mass timber elements. And really, I'm going to talk mostly about panels. And in fact, what you'll hear me saying all the time is CLT. But in fact, I think you know that there are quite a variety of panel products that are out there. We've used, I think, most of them. And I don't think there's anything I'm talking about that wouldn't apply generically or more broadly to all of those panels. So forgive me for just saying CLT. My first slide, since I'm going to talk about cost, I thought I should start by talking about the commodity element of a mass timber. CLT is made up of lumber, and lumber prices go up, they go down, they're going up and down probably even as we speak today. It can be very, very dramatic. And that's another way of saying that as I go through this presentation, I'm going to show you dollar per square foot costs of mass timber structures and other kinds of structures. And this slide tells you don't believe it for a second in terms of the actual final cost. Because even, I mean, a lot of the numbers I put together were put together maybe 2 years ago now. So the prices themselves are irrelevant, but hopefully the relative comparison between different systems using the same price basis will still be relevant, okay? So CLT cost also depends on supply, which is growing, which is good news. And you've heard a little bit about that yesterday. And this one I'll stop on for a moment, that CLT cost depends on wood volume. And I've just always really liked this slide, which I think I stole from Woodworks, that it just really exemplifies how much wood goes into, say, a 9-ply layer of a panel of CLT. I'm used to pricing steel structures. Steel structures are driven pretty much by labor. 2/3 of the cost labor, 1/3 of it is material. For mass timber, it's the other way around, and even exaggerated a little bit. I don't know what the fraction is, but it might be 80% material and 20% labor, or even more. So as we go through, we'll find and that's actually kind of good news for designers, because it's easy to keep your eye on wood volume and know that if you decrease the wood volume, you'll be decreasing the price. We've worked on our end to try to get floors and roofs down to 3-ply wherever we can. At the end, when we get start talking about carbon a little bit, it goes the other way. Of course, that 9-ply CLT sequesters a lot of carbon, but we're starting out talking about cost. The other thing is that CLT is really not a commodity. It's made in a lot of different places. Each manufacturer does it a slightly different way. They have different widths, they have different lengths, different lamination thicknesses, species, finishes. It's, you know, it's really quite a dramatic variety. So you cannot treat it like you're ordering a sheet of gypboard, right? At the end of the day, you're going to find that the best way to understand or to truly optimize the price is to find a way to be sitting with the manufacturer as early as possible in the process, or the fabricator, the people that are actually going to build the structure. I'm pretty sure that Lucas will back me up on this. His group actually supplies that kind of information early on. And the earlier you can get to the table and know the specifics about their product, the cheaper you'll be able to make it. So here's one specific example of that. This is a plot that shows the cost of CLT for different volumes, 3, 5, 7, and 9, or 3, 5, 7, and 9, with the cost per square foot over here, and then the required panel length. And you'll notice that there's this sort of sawtooth pattern that comes from the difference between the required panel length and the press length that a particular manufacturer might normally make. So in some cases, like in this case, around 25 feet, as based on the press length that is used, it's either 30 or 24.7, you're going to leave a lot of CLT panels sitting on the shop floor. And by the way, you're going to pay for it, whether it's sitting on the floor or in your building. This diagram itself came from a real manufacturer, but I'm pretty sure, again, like the cost, that this does not apply in terms of these numbers, or even in terms of their press panel lengths anymore, even for that manufacturer. So again, this is something that you need to get or understand from, or just be counseled by the fabricators themselves. And likewise, glulam and column costs that form a part of the following studies are just unit costs. Some people find it interesting, myself included, that the unit cost of glulam, the cost per cubic foot, is actually dependent on the width. So the wider the beam is, the larger the cost per volume is. So it's not just linear with wood volume. So that's an interesting point. So now let's take that information and move it forward and look at the cost of just some very, very simple bays, square rectangular bays. And this goes back to a study I did a couple of years ago now. Just very, very simple minded. I framed out a typical bay, starting with 15 by 15, and then I increased the beam lengths up to 30 feet. Then I went back and increased the girder length up to 20, and increased the beams again, and so on down the line until we got up to 30 by 30. Then I applied all those rules for cost of the elements based on volume and so on. And I made this plot, which shows the cost per square foot for each of those different grid sizes, one by one. The brown section of the bar represents the cost of the wood. The red represents the cost of connections, and the gray is constant because that's the cost of the topping, which I didn't change for any of those. Interesting to note, although I'm not going to go into it today, is that the percentage of the cost of the whole thing that is connection is significant. So connection design, while I'm not going to talk about it, is super important. Another piece of data here is this orange line, which goes along with the right-hand side. And that's telling me the clear height for a 12-foot floor-to-floor to the bottom of the beam. So you can see, obviously, the longer the span, the deeper the beam, the closer you are to knocking your head when you get to the end. What's most interesting to me about this plot actually shows up when it's shown relative to another one. This is an identical base study, but in this one, I use steel beams, girders, and columns to make a hybrid system in CLT floors. In that system, this one shows the same. The wood is the wood cost, or excuse me, the brown is the wood cost. The blue is the steel cost, and the gray constant again is just the concrete popping. You'll see here this little bump actually is that 25-foot realm that I showed you, where I'm paying a price for having an inefficient panel length relative to my fictitious manufacturer. The other thing that's interesting is that there's this sawtooth shape, and for steel, it goes down to the right, down to the right, and down to the right. And this is because steel really loves long spans and fewer number of pieces to carry that span. That's how steel works. The sawtooth on the wood side is going very much the other direction. So it's a completely opposite dynamic in terms of the cost. And what that means is that if you pick an optimal grid for your steel structure, and then you go to look at a wood alternative for it, if you assume the same grids as steel, you are not going to find the same optimum as you would for the wood structure. Sherry brought this up yesterday, which is don't start with a steel building and then superimpose a wood idea. Wood needs to be designed as wood. Going back to Louis Kahn, what does steel want to do and how does it work? What does wood want to do and how does it work? If you want a cost-effective wood building, design a wood building. Don't put some wood icing on a steel structure. So moving to my next type, I took that same study, that same basic logic, and then wanted to apply it to more building systems. That last study really only involved type 3B unrated structures. And I wanted to see what the effect of all the new type 4 building types and even type 3A and B for multi-story structures was. To do that, I went to across the street from my office to the Colorado School of Mines and enlisted the help of Professor Xiling Pei and his student Rachel Chigaris. And they were much smarter and more efficient than me. And we developed some programs to do what I had done by hand and to do it relatively quickly. So the big difference between this study and the last one I showed you is now we're incorporating fire rating requirements, which have a real effect on the volume of wood if you're using the wood to create the fire resistance, and also non-combustible protection that is required for certain of the type 4 systems. So having done that, the good folks at the School of Mines now went in and instead of just doing a relatively, checking grids every 5 foot on center, they've got a computer to do it and check the grids every 6 inches, right? And so they developed a contour map of cost. This is the 2D version, and then this is a 3D version of the same thing. And you can kind of see these mountains of cost variation for different grid sizes. There's some really interesting, patterns that grow out of this. Like one is you see these sort of diagonal ridges that show up. Those pretty much represent increase in connection cost as the beam and girder reactions go up. That was kind of interesting. And then another thing that's a little bit more obvious, you'll recognize this picture because we talked about it before, and you see that mapping of the press length versus the required panel length just superimposes itself over everything. So once again, this thing, which is unique to the manufacturing process, has a profound effect on the cost and even your choice of a grid. So again, you really want to engage manufacturers, fabricators, builders pretty early on. So taking that same study and extrapolating it to all 6 different building types, we actually have dozens of these graphs for different types. I kind of mixed and matched a few here, but this is working from type 3B through type 3A and then up into the new type 4 HT, C, B, and A. And I'm kind of working my way up in cost. As you can see, the cost, these are all to the same scale. So the cost kind of goes up and up as fire rating requirements go up and as requirements for non-combustible covering go up as well. This is kind of interesting in that this one is a floor that's made with 3-ply CLT and this with 5-ply CLT, but this has limited gyp covering, and this has 3 layers of gyp covering all over it. So this is a little bit more expensive, but a lot more wood in the Type 4B system. And again, you see some of these same patterns. Here's that press length pattern. Here's a step up actually when we added a beam to the grid to deal with the longer spans. Here's the diagonals that are associated with column, connections and increasing reactions. Just kind of a lot of fun pictures. Another fun study that came out of it was to look at like a 6-story building and as Drew said yesterday, what, even choosing your building type will affect ultimately the cost, right? So this is asked the question, for a 6-story building, what grid, for different grid sizes in a 6-story building, which building type is the least expensive? So using the number 1 to represent 3A and the number 6 to represent 4HT, it shows you there's this zone where the 4HT is actually more economical than a Type 3A structure. We did a pile of these as well. It's pretty interesting. And then finally, this is kind of a summary where we took these hundreds of analyses and said, what was the cheapest grid size for each building type? And I split here in between Type 3A with gyp, providing the fire rating resistance for the floor, and with no gyp, so the wood provides the fire rating resistance. So what's interesting here is that there's kind of a different optimum grid. If you want to say the optimum grid for timber is 20 by 20 or 24 by 24, really it depends on the building type, the number of stories. You can also see pretty clearly what we know generally from buildings in general, that if you start at the left and work your way up, you will have the cheapest structure. If it fits in the 3B category, put it there. If you have to go up to 3A, put it there. Going up to 4C, so in my example then, if I could do a 6-story building in one of these 3 types, I wouldn't probably elect to make it a Type 4C until I wanted to make it 8 or 9 stories. And there's just kind of a 3D map of that same data, just showing for a certain number of stories and building type, what the cost relationships are per square foot. You'll see that again here in a minute. So now let's look at full building archetypes. This time we looked at an entire building. This is a mass timber building on a 30 by 30 grid. It's a totally idealized rectangular building like an engineer would design, not a good architect, but that wasn't the point. We designed the same one in steel, concrete, and mass timber. And despite what I just told you about optimizing grids, we used the same one for all these 3 buildings, thinking that that was a pretty good middle of the road grid that should work for all of them. And then we went to a real contractor, the contractor that built the Plat 15 project here in Denver, and had them price these options out. And this is actually the slide that I mentioned that the presentation is born out of frustration a little bit. And this is it, encapsulated. And I've known a lot of people that have seen this over and over again. So in this case, in this market, when we priced this is now about a year ago, it just happened that the concrete was the cheapest structure in Denver at that time. And the steel structure was a 4.5% premium over the concrete structure. And the mass timber raw material installed was about a 14% increase. And this is the point when the developer says, boy, I sure would like to use mass timber, but that's just too much to pay. So it gets taken off the table. In fact, this number, talking to some folks around the country, is actually not that far off base. I've seen it a lot of times. So as I said, though, the contractor that built, that did the pricing had built mass timber structures. And he said, wait a minute, let's look at how quickly this structure goes up and see if we can quantify that. And as it happened, by their estimate, the wood structure would have gone up 3.25 months faster than the other 2 structures. So that time relates directly to the value. So this plot shows really a number of different passes of cost estimates on exactly the same structure, but including different scope in the cost estimate. So this is a typical schematic design level cost estimate, raw material installed. But if we include that 3 months general conditions, the cost of labor, and take that cost out, it cuts that premium in half for the mass timber structure. If you go further, include general requirements, equipment, waste management, and so on, it cuts it down again to about a 2.4%. Urban site logistics, other things that relate to time. And now I cheated a little bit, stepped outside the realm of structure and said, gee, the wood doesn't need any ceiling finishes, but these guys do. Really, actually, now the wood structure is ahead of the steel structure, and it's getting down to some pretty reasonable numbers. And this is just superstructure cost, right? For a typical building, you know, the superstructure might be 15% of the whole building cost. And if I look at this premium for mass timber relative to the whole building cost, in this case, it went down to near zero. Now, I will point out that this is a very idealized engineering blocky building. It has multiple stories. It's very repeatable. It can very much capitalize on the speed of construction. So I might be tilting in favor of the wood structure here, but still these numbers get you down into the zone where you can have a discussion. So with that, I want to switch quickly to the notion of carbon. Many people have talked about it in much greater detail than I can or will, but I like to make it a part of every conversation now, right? So we saw before for my study of building types and stories, this is the cost numbers. This is the same picture you saw before. We went and did LCAs just on the structural system itself, just on the wood volume only for those same systems. And here's the global warming potential cost, which I put in quotes because of course it's negative. So it's really quite a benefit. So what I wanted to know is you know, can we capitalize on that? Can we convince owners, people that are buying the buildings, to recognize the value that they're getting for this extra cost? Okay. Back to my archetypes, this is a kind of diagram you've all seen a million times. We did the LCAs for all these different building types. And as usual, concrete's the winner, quote unquote. Steel a little bit behind that. And the wood variations that we looked at were all the least global warming potential of these. Not negative in this case, because I'm not including the sequestered carbon. So in any case, here's a value, right? And we want to assign a price to that. So I'm back to my curve about what the premium is, and just forget the timing for a moment. Let's just say we're down into the 1% to 2% level. How do we jump that gap? And with that, I would introduce a group that we've been working with for the last couple of months, Aureus Earth. I want to say they're out of Boulder because my friend Will Shrubar is in Boulder. He teaches at University of Colorado, but my only meetings with them have been over Zoom. So in truth, I have no idea where they are. They are the world's first carbon marketplace for buildings, for individual buildings. So they have set up a business to try to monetize that value. And this slide is impossible to understand, but let me just point out that they get in touch, they act as a broker. This is Aureus Earth from a buyer. Then they go and work with the design team like us, particularly in the very early stages of the project. They take back information in terms of what embodied carbon we saved as a result of design choices. Design choices say, for example, like going to mass timber instead of steel construction. They then sell that carbon offset to a buyer and return that money to the builder. It's actually at no cost to the builder. It's a really interesting system. First building we looked at, it was a very small building with just a very little bit of mass timber in it, and it was kind of disappointing. The benefit is about, I don't know, 50 cents a square foot on the building. But we're looking at one now, a 200,000 square foot mass timber building that may well benefit to the tune of $2 a square foot from this process. So that doesn't completely cover the difference in the cost of mass timber, but it certainly opens the developer's eyes. So that's a hopeful note. So a quick summary, looking at elements, we learned that mass timber is not commodified. Get to know your manufacturers. bays, the optimal bays are not the same for steel or concrete. When we look at different building types, generally in order of increasing costs, start with 3B and work your way up to 4A, about in that order. And then the building architects taught us that timber is most competitive when the speed advantage can be recognized. So multi-story buildings with some repeatability. And then finally, the carbon advantage of mass timber may now be able to help close the gap through carbon offsets, which is a truly monetized way to represent the value. So thank you very much. And with that, I will stop sharing and turn the podium over to Lucas.
Great, thanks, Greg. That's a really cool study. I hadn't realized you guys had done so much work in that space and figuring out the cost efficiency of mass timber. It's some really amazing insights in there. Thanks for sharing that. It's really cool. Okay, I'm just going to share my screen here. Give me a second. Is this coming through? Or maybe not yet. Does this work?
Yep.
That worked.
Okay, great. Awesome. Thank you. So today I'm just going to talk a little bit about some of the timber engineering that we've had the privilege of getting involved with in some of our past projects, and really where we see the next boundaries in timber engineering, both in the mass timber space and then also in some more of the longer span free-form type structure space. Our company, StructureCraft, we're structural engineers and builders. Similar to Greg, we got this kind of integrated approach to looking at both the engineering and also the construction side of things. So first today, I wanted to talk a little bit about mass timber, and in particular, a brief little history thing, and then looking at the core systems for mass timber and what the different types of core systems are from a topology or a typology perspective. History of mass timber, obviously most of you will be aware of the strong history we have here in the US and Canada of actually building these really big mass timber buildings. These heavy timber, brick and timber, mill timber buildings that use the solid laminated deck and these beautiful old solid sawn Douglas fir beams and columns, creating this aesthetic that we see in the warehouse districts of many of the cities across North America. And I like to show this building in Minneapolis because it's 5 minutes down the road from the first really big mass timber project I was involved with, which is the T3 building in Minneapolis. This is called the Butler building in Minneapolis, and it's really quite an incredible structure. It's 500,000 square feet and 9 stories tall, and it was built back in 1907. And to date, there's not a single mass timber building in the US that's bigger than this. There's just about to be one that's taller than this. It's under construction right now, or a couple in Milwaukee and Cleveland. But this kind of behemoth of a mass timber structure from more than 100 years ago still stands out as an achievement to what we as a society were able to achieve with timber structures back in the day. And it's good to look back to look forward. And so these old buildings, they use these huge, like I was saying, solid sawn timbers out of logs that we don't chop down today, and we shouldn't be chopping down today. But now what's really enabled the next generation of timber structures is this idea of engineered wood products, CLT, glulam, and you've heard about it. So today I just want to focus on core systems and look at some of the different options in terms of lateral force resisting systems for these mass timber buildings. And I'll do that through a series of really quick case studies. This little diagram here is looking at CLT cores for a project we're doing in Baltimore right now. So we're going to be using CLT cores, and CLT, uses, like Greg was saying, it uses a decent amount of material, and like he was saying, the wood, the component, the wood material becomes a large portion of the cost. So figuring out how to get your wood volumes down is really important. I'll start with concrete cores. This is the first T3 in Minneapolis, which is really, a very simple structure. From a structural standpoint, it's a concrete core, and the mass timber superstructure that surrounds it is a gravity post and beam. On Greg's plots there, this would land in at about the 20 by 25 foot grid mark. So a very simple structural system, prefabricated elements. And the real challenge here from a construction standpoint is the concrete core is going up at the same time as your mass timber is going up. And so what that means is if you've only got one tower crane on your site, one of the big challenges is how do you erect both structures at the same time? And so I show this because I'll show the next T3 we did, which uses a different lateral force resisting system, which is more integrated with the mass timber. But I think the concrete core, the great thing about that, particularly in the high seismic regions, is that you've got a very well-known material, very well recognized and accepted in the building codes. And so there's definitely a place for concrete cores. And we're still doing quite a few projects which have concrete cores. So it really depends where the project is. And but this project here was done 2014, 2015-ish. And it was kind of one of the first big ones we had done, and the concrete core seemed an obvious choice at the time. This is with MKA, was the engineer of record in this project, and we were kind of doing all the detailed timber engineering for the timber structure. And of course, the sustainability Greg mentioned, this idea that we lock the carbon into the structure is a key part of why we see developers like Hines wanting to proliferate these big massive timber buildings around North America. The second T3 building in Atlanta, which was recently finished, I guess maybe about a year and a half ago now, is actually using a steel brace frame. And so this idea, you can kind of see in this little animation, that we can take the lateral system off the critical path of going vertical with the superstructure. In this case, the steel frame is a hybridized frame, steel braces and timber columns, and that creates what we found to be a really efficient system. We're able to install the bracing system off the critical path of the superstructure. Definitely made the install go faster, and I think also, the prefabricated nature of the steel frame lends itself a little bit more to the way mass timber is, this kit of Lego that comes together on the project site. Integration with mechanical in this, now that we're using a steel brace frame, inside the core is all timber. It's not concrete anymore. So you got to think about how you're running all your services through the timber. So, prefabricating and looking at how the mechanical runs and all that stuff is coordinated into the timber structures is super important. Even more so when you're not doing your core out of concrete anymore, you're doing it out of timber with some steel. So that's a quick look at a steel brace frame. This project is in San Antonio with Lake Flato, and we were the engineer of record on the structure. And this is using a concrete core again, but using wood in some areas here. You can kind of see we're transferring out an entire column from a gravity perspective onto a series of braces, which also act from a lateral perspective. And here, one of the interesting innovations is using a raised floor. And we're seeing that more and more people are interested in raised floors, now that we're looking at a post-COVID marketplace in terms of air distribution, et cetera. So this is our kind of 3D fabrication level of detail model with all the screws, et cetera. And then one of the construction shots in the finished building is also supporting brick off the mass timber, which is quite a tricky thing when you're looking at brick and supporting off the timber, which tends to creep over time. Brick is quite a deflection sensitive material, so something that requires some careful detailing. There's another big residential project actually down South America we're involved with right now, which is looking at, from a residential perspective, how do we use mass timber? And we're actually looking at point supported CLT for a 2-hour fire rating. So exposed CLT for 2 hours of fire and using point supports. So really, that'll be really quite an innovative project because most of the time when you're doing the point supported CLT, the CLT is then covered with gypsum to achieve the 2-hour rating. Here, a project in Des Moines, Iowa, where the mass timber is kind of integrated with a precast core system. So sometimes precast can make a lot of sense as well. Here we've got the series of precast core components along the backside of the building and the prefabricated mass timber, allowing the whole superstructure system, even though you're doing concrete and timber, you're still all prefabricated. Came together really quickly, and I think in some some regions, and this type of a lateral system can make a lot of sense. Finished project. And finally, just a look at the lower level multifamily, or in this case, this is a hotel project in Austin, Texas, where we're combining kind of a mass timber roof and floor system with prefabricated stick frame walls. This can also be really cost effective depending on, like Greg was mentioning earlier, which kind of building type you're in and the size and height. Obviously once you get past around 6 stories, the stick frame doesn't make sense and not even really achievable from a code perspective. But this idea of prefab stick frame with prefab mass timber floor and roof panels can be quite cost effective, and actually it can be really, I think, the right answer for some of the residential, and this is a high-end hotel. But this idea of having the stick frame allows you to have a lot more mechanical services integration. Also, the stick frame walls from a structural perspective act as your shear walls. So you're not dealing with, the other option is to do a honeycomb, what we call honeycomb structure, where you're doing solid CLT walls and solid CLT panels, and that's done in Europe a lot. But what we see here in North America, because the cost of these structures is so highly driven by the volume of wood, that doing solid wood panels often doesn't make sense from a cost perspective, and the studs, the prefabricated stud type structure actually enables you to do more routing of services and have more flexibility and not have to have double solid walls, etc. So this project also had a series of kind of walkways along the exterior, which is kind of more of a post beam type structure, which kind of connects all the different hotel units, and this is just a look at some of the connections, etc. But the neat thing, I think, about the mass timber on the stick frame is that the mass timber inside these hotel rooms or inside these spaces gives you this beautiful aesthetic, and that's really what we're seeing developers and owners and architects they're really after, is really having a beautiful aesthetic that they can sell as a differentiator in the marketplace. So we see the mass timber on stick frame being a real contender in some of the building use types. Just some finished photos of that particular project. Now I want to talk a little bit about another thing which tends to drive cost and structural design on these floor systems. And when we as structural engineers are looking at a mass timber floor plate, say for an office building or even residential, what typically governs our design isn't actually the structural design of the elements. Like, in other words, making sure that the beam or the column or the floor panel doesn't fail in bending or shear. What's really governing us actually is how bouncy the floor systems are. And that's an area that there's a lot of work being done by a lot of the leading engineers, including Greg's firm and others. And we've been part of this, writing this new mass timber floor vibration guide for woodworks, which is going to come out, I think, later this year, to really look at how do you deal with this issue of floor vibration, because it really does govern how much wood volume you have in your structure. And so one of the things that we've been looking at internally is kind of a parametric tool to allow us to look at the vibration response of these mass timber floor plates kind of parametrically, so that we see how different floor plates and grids and spans and thicknesses of panels change our floor performance. And in this case, this is looking at plotting the acceleration on the floor plate as somebody walks on it as your grid and base size is changing. So that's a little bit of a look at mass timber and some of the kind of different core systems that we're seeing come into the fore. And now I'll just talk a brief little bit about freeforms and longer span structures and what we see as an opportunity there for really pushing the limits with timber engineering. I'm just going to use a project we recently finished in China as an example of where we can really push timber to its limits. We're seeing architects all across the world see timber as the new material of the 21st century. And they're starting to say, well, hey, if I can do big, crazy structures with steel, why can't I do it with timber too? And the answer is you can, but it does require outside the box thinking, and also owners and architects who are willing to kind of push their stereotypical concepts of what might be achievable with a material like steel in these longer span structures to look at what timber can really achieve. This is a series of 3 grid shells in Taiwan and China. They're greenhouses, And the challenge put out to us by the architect was to create these all timber grid shells. And they're up to about 300-foot clear span, the largest one, so really big clear span structures. And of their type, it might be the largest timber grid shells in the world because they've only got timber elements in two directions, so they're not triangulated. So to just give you a bit of a background on some of these longer span structures that have been done here in the U.S., many of you guys will be familiar with the Tacoma Dome or Superior Dome. Superior Dome is actually the largest span timber structure in the world that I know of right now at 163 meters, built back in the 90s. And these structures were actually all built kind of using these triangulated, reticulated type topologies across a spherical cap. So they're sections of a sphere, the geometries of these roof structures. And on this project in China, the architect from Vienna was pushing us to look at a grid structure which actually only had elements in two directions, not three. So it's not triangulated, it's actually just got quads as a geometry. And from a structural engineering perspective, that's actually quite challenging. If you look at the steel grid shells that are all over the place, the Smithsonian or British Museum, you see the steel that's welded to each other kind of to create this very stiff joint between the two layers of the two directions of the steel grid shell. Here with timber, you can't weld timber, at least not that I know of. And so if you can't weld it, how do you fix it together? How do you create this moment capacity between the different directions? And you need that fixity because otherwise you get what we call in-plane shear buckling of the shell. And so these are the three grid shells in the structure. The biggest one is about 300-foot clear span. And the biggest two, we used a 3-layer grid shell, and the smallest one was only 2 layers. And so one of the big challenges was the geometry and looking at how to rationalize the manufacturing process of these shells. And if you look at a pattern on top of this is kind of an ellipsoid almost. And if you look at kind of putting a radial and tangential pattern onto this of geometry onto this shell, you end up with a geometry which looks pretty simple in plan view. But actually, if you take a piece of glue lam along each of these lines and you kind of look at it by itself, you'll realize that it's actually doubly curved. That adds a lot of complexity to the fabrication and also really limits. There's only about 2 manufacturers worldwide who can press an initially doubly curved billet of glue lam. So we as engineers, we had to find a different way of rationalizing, kind of removing some of that double curvature. And so what we actually did is we looked back at some of the work that Bucky Fuller did back in the 60s and 70s on these so-called Bucky domes. And it's a way of patterning a surface with what we call geodesics, which is a geodesic sounds like a complex term, but it's a geometry term for a curve which just connects the 2 points in a surface by the shortest path between them. And so Bucky Fuller, he patterned these spheres with these elements which went along the path, which are called geodesics. And like for example, when we fly across the world, which none of us do anymore, but when we fly, we would obviously fly along geodesics along the Earth because that's the shortest path between the 2 points. And so what we actually looked at doing was taking this geometry and creating a geodesic grid. So each of these lines that you see here are now the shortest path between the 2 endpoints. What that does is actually turns the doubly curved glue lam into singly curved glue lam. But from an architectural perspective, we had to do a kind of a tweaked version of that to achieve the openings. And so we're able to kind of remove a lot of the doubly curved glue lam, but there still is in the kind of radial direction, some doubly curved glue lam in the structure. Now to analyze these structures, you need a parametric approach. So this is using Rhino and Grasshopper and computational design to look at different grids, different densities of patterns on the shell. And then looking at all the different wind load directions, for example, applied on the shell. So this computational design approach is critical to achieving the longer span structures. And here there's a little diagram kind of showing I mentioned this kind of for the engineers in the audience, this in-plane shear buckling phenomenon, which you can see in the right here. And this is the type of buckling shape, greatly magnified that you would see were you not to be able to achieve moment fixity between your 2 directions. So what we had to do is look at connection design and small scale testing and full scale testing at our shop. This is some pictures of some structural testing we did. We've got a strong floor at our shop, and we kind of take some of our connections that we're designing through to failure and look at what the structural capacity of these joints is, and then what the actual stiffness of the joints is. So that gives us the confidence for developing these kind of joints and knowing how they're going to perform in our structural finite element analysis models. So we take those kind of small scale tests, put them back into the finite element model, and then calibrate that and check the overall structural performance. Some of the testing for this particular project we also did in China, Tongji University, to demonstrate to the local authorities the adequacy of the different connections we're proposing. But also from an engineering perspective, one of the big challenges is fabrication. I mentioned this whole idea of doubly curved. We worked with 2 different European glulam manufacturers to make all the several thousand cubic meters of glulam required for this structure. That was a big challenge. We're actually taking our Rhino models and we're going straight to CNC files. So we developed our own custom kind of, I guess you could call them libraries, to allow us to go to the CNC file level from our Rhino models. And that's really key. And that's also what some of the Europeans are doing for some of the larger scale kind of freeform timber structures that we see happening in Europe, like the Swatch building, et cetera. So here you see one of the first domes completed, and in the background you can see what is a sea of scaffolding. And our original concept for installing these structures used these shoring towers, which quickly got thrown out and got replaced by a crazy mountain of scaffolding, which I almost couldn't believe that this would be the most cost-effective way to do it. Pretty certain that wouldn't be the case here in North America, but in China this is the best way of doing it, and the cheapest way, and probably in the end the safest way, given the way the way things work there. So here you can see the prefabricated approach. So when you're engineering these structures, it's not just about making sure and checking your structural capacity. It's about how do you actually manufacture it? How do you assemble it? How do you install it? And so here you see this concept of breaking this shell down into prefabricated panels. And these panels all come in a sequence, and they're prefabricated, close to adjacent to the actual construction site, and then flown into place. So this is the kind of Rhino fabrication model, and then through to the finished smallest shell here. You can see some of these panels flying into place. Shop drawings also important, also coming straight from Rhino. And here what we're actually doing is we're using what we call block glued glulam from Europe. So it's double wide glulam, which is then CNC'd in both directions to create the double curvature. And this doubly curved glulam element is then part of a larger scale panel. And this prefabricated panel is what goes then and gets installed onto the timber structure. So this idea of prefabrication, even when you're in an on-site setting, is key. So this is the largest shell here, which you can see this kind of diagonalized cable stiffening grid, which we used on the largest of the 3 shells. The 2 smaller shells actually didn't use any cables to provide stiffening. They're just using the moment connection between the timber joints. So prefabricating, but then also looking at binning all of the glulam into different radius bins so that we can optimize and not have every single one of the several thousand pieces of glulam have to have a different press setup. Even in Europe, where all the press setting up for the curved glulam is fully automated, it's still a lot of work to have to change the press setup for every piece. So you have to reduce the number of press setups. That's key when you're doing these more free-form structures. These are some of the panel shop drawings for each of the different panels, prefabricated panels that go across the shell. And then logistics, another challenge when you're getting product from Europe, shipping it to China, you got to plan it very, very accurately. So this is looking at packing all these glulam pieces into shipping containers, doubly curved, singly curved, and figuring out where each of the elements go, which level they're going to be on, how they're going to get shipped to the project site. Pulling some of the glulam out of the container and some of the coating. And on the largest dome, we used a cable net, which I want to talk briefly about because that was a really interesting challenge. And we talk about timber engineering, and sometimes I think to myself, actually, it's steel engineering. Well, it's timber engineering, but it's using steel. Many engineers often say that timber structures are a bunch of connections held together by timber elements. And what they mean is that the connections are the biggest and most important part of any timber structure. How you achieve the connections is really what drives the success of your structures. And here on this biggest dome here, we had to use this diagonal grid of cables to stiffen the shell, the timber shell. And the big challenge that we had here is coming up with a connection between the cable net underneath the grid shell and the grid shell above. And you can kind of see this casting node that was developed in close design collaboration with the architect, but basically connecting all these cables, which kind of cross at different angles up to the timber structure above. We had to achieve a shear stiff connection between the cable net and the timber structure above. And so to do that, there's a really interesting concept devised, which basically uses these decoupled castings to connect each of the cables together. These castings are kind of threaded onto a central threaded rod. The central threaded rod then, once everything's in place, is basically tightened towards the grid shell structure. And what that does is that process of tightening it towards the shell actually induces tension into the whole cable net. So that's how we were able to kind of, pardon me, tension the net, as it were. This is some of the early mock-ups of this stainless steel casting, and some pictures you can start to see of the shells as they were during construction before the glass started to go on. The glasses kind of stood off a little bit, so it lends a little bit more visual depth to the structure once it's completed. So this is the structure finished about maybe 6 or 8 months ago. And some shots from the interior of the three different biomes, like a tropical dome, desert dome, aquatic dome. So different plants and all sorts of different, even just different relative humidities and temperatures inside each of these three shells. So yeah, a really neat project, and I think, a tribute to what can be achieved with timber. So when you're conceiving your next timber project, let imagination be your limit. I firmly believe there is no limits to what's achievable with wood. It's a beautiful material, it's a natural material, and I think something that we should all be investigating with as we move forward into the next generation of construction. So with that, I'll stop and hand it back over. I don't know, Shauna or.
Yeah, thank you. Thanks, Lucas, Peng, and Greg. I just want to say that we have some questions, queued up here, but I want to encourage the audience members to provide more questions. I think you guys' presentation did a great job of providing a cross-section of the material tectonics, possible from within the industry, but also then the very specific, project that you shared, Lucas. That was great. One of the questions earlier that we had in a different panel was about, is working with wood or the CLT, mass timber sort of limiting in terms of form? Is everything going to be boxy? So I think you just answered that question, blew it out of the water, and anything is possible. One common theme that we're seeing, across the discussions, and I think it was interesting how each of you addressed it, was this idea of optimization. So last night in our keynote speaker, we had Alan Organsky, and Tom Chung asked a question, who's working on many of these buildings across the US, what is the optimal scale of some of our buildings? So it was great today to see sort of how they perform optimally, presented by Peng, and Greg, how you're looking at, really the economics of maybe what some of those optimal scales are. And then Lucas, you really dug in terms of optimizing, sort of a specific performance for the project. So I think that's a great place to start. And one question I wanted to read here that, on that idea of optimization, it's Greg, the question says, understanding that this was a dollar costing investigation, did you compare CO2 footprint differences between types like 4A and 5B, unprotected versus gypsum protected? And that's a very specific, CO2 question, but I want to open it up to the three of you to say, while we're thinking about cost, and at some moments you're talking about structural capacity, but what are some of those other parameters that we're looking to optimize along with the material tectonics?
To jump on that one first, that was actually one of the slides that I took out of my presentation, trying to trim some time out of it. If I may, I'll share my screen again just for a minute to show you that
Sure.
this is the same. Wait, hang on. This is the same study that I did for the cost for these different grids, and whoops, hang on. This is this shows the global warming potential by building type for just the different. And again, these are only one example, which is the least expensive of the different building types that we looked at for each story height. So it's only one example of one building. And we went ahead and did the global warming potential analysis of those. And it's, it's just interesting to see the trends. Some of these go up and down based on the nature of the grid changing. Some of them go up and down as I see it as the fire resistance goes up. And then here we go from 3-ply CLT to 5 covered with GIP, and then down again is the 3-ply covered with even more GIP. But this is the GWP, not accounting for the sequestered carbon. If I take it one step further and look just at the sequestered carbon, you get a bunch of big negative numbers that kind of are the inverse of the cost structure. So here are type 4B, which looks very expensive on paper in terms of dollars, looks like a great carbon sequestration vehicle. And then if I add those together, I end up with this final plot that I did show you before. So yes, we did look into that, but I can't say that I have any. We're still actually digging through the data. This is pretty recent. So I'm really kind of anxious to figure out, exactly where we go from here. But yeah, that's the way we kind of look at everything now in terms of there's a dollar cost and there's a carbon cost or a carbon benefit, and how do we connect those in terms of value?
Great. Lucas or Peng, do you want to add on to that in terms of maybe some of the other parameters that when you're doing these studies you're engaging?
Well, I don't have much to add to what Greg just mentioned.
The I'll throw in that in your original question, it seemed like like I was hearing kind of what's the sweet spot for mass timber and so on, and I'm not sure I know the answer to that yet. Like Lucas showed a really great project that was a really small hotel / storm project with a hybrid of systems and so on. That looks really promising to me, but we haven't seen enough of them built to really know if that's going to play out. But my guess is we're going to see a lot of mass timber buildings that are between 6 and 9 stories based on the new codes, because I think that's the sweet spot, and I think it's going to slow down for the 12 and 8. We're not going to see a lot of 18-story timber buildings for a while, but I hope we cover the landscape with 8 and 9 story.
Yeah, I tend to agree with you, Greg. I think the challenges around having to cover the wood, although I think that's starting to be addressed. In Canada, for example, there's some research that's being done, and I think there's going to be a bit of a removal of that requirement for some of the taller wood buildings. So I think we may see some changes in the building code over the next 10-15 years, which enable higher buildings without having to cover absolutely everything. But I agree for the next few years, that's going to be a big push in the lower range, I think.
But I'm imagining having a lot of intimate conversations with building officials about the type 4B structure and trying to minimize the amount of coverage that you get there. And so we'll see how that goes.
Well, on that note, I think it was a similar process, when they changed the code to allow the 5/1s, there was a lot of conversations in terms of when we have the light wood framing, how do we have connections or joints, and either, fireproof those connections, et cetera. So I see it definitely being a dialogue going back and forth. But maybe sort of approaching it from a different scale too. One of the questions says, if we bring mass timber product production to smaller secondary timber processors, like millwork shops, regional fabricators, via products like the mass plywood panel, Would this offer a more regional expansion of mass timber? If so, would this ultimately provide a more economical cost for residential mass timber builds? That's specific to, you know, a residence, but I think what I'm interested in that question from the audience is, you know, how do we, you know, like you said, Greg, cover the landscape with these buildings, knowing that we have sort of, you know, limited manufacturers right now and infrastructure and logistics. How do you guys envision the industry becoming more nimble and allowing some of this sort of regional production?
Well, I think, you know, I'm going to try to kind of give you my thought here. I think definitely, you know, if you have more production spread out in the US and you can easily access to the CLT, it's going to reduce the cost. Actually, we have an ongoing project looking into using CLT as a noise barrier along the highway. And we performed a study by comparing it to using concrete, precast concrete panel. Usually those are the noise barrier used along the highway. And we quickly find out, you know, the shipping cost is one of the major issue because you cannot get CLT panel within, you know, let's say 100 mile radius anywhere in the US because we only have limited site here. But for concrete noise barrier, my understanding here is anything kind of more than 100 mile radius, it is not worth it to ship it. So I think, you know, if you have more smaller production, I think it will drive down the cost for residential or for any project, in my opinion.
I want to actually direct a question to Lucas because your firm has a lot of success with nail laminated timber in the history and now dow laminated timber, but the nail laminated is kind of the low tech version of mass timber and famously one of the most more least expensive and requiring mostly local, you know, you don't need quite the equipment and infrastructure investment that you do for CLT. I wonder if you might comment on that.
Mm-hmm. Yeah. Yeah, the NLT is, like, I see as it's certainly something that enables people who want to get in to get in. And it's something that, you know, we pushed a lot of, I would say 10 years ago-ish, to try to see if we could use that product as something to kind of kickstart the mass timber industry and say, hey, you know, we don't have to wait for one or two CLT manufacturers or somebody from Europe to ship stuff. We can really figure out a way to do it here and do it locally. In fact, that first T3 building I showed you was done with nail laminated timber, all done just, you know, a few hours drive away from Minneapolis. It was just across the border in Canada, but you know, that idea that you can fabricate locally is certainly a powerful one. You know, NLT has some challenges at scale because you've got all the nails, you can't really CNC it. It's difficult to scale up to huge projects, but I think at a local scale, he wanted to do smaller stuff. You know, we still see NLT projects going on all the time here in BC and Canada, and I'm sure it's happening all over the US as well. But I think the other thing to be encouraged about is we're seeing a lot more manufacturers come online. You know, in Texas, Arkansas, you know, all over the place, we're seeing new manufacturers come online. And so this issue of, you know, having to ship, you know, the carbon implications of having to ship from one coast to the other, stuff like that are starting to be reduced. And, you know, I think that's a key, is getting more production online, which I think is really starting to happen.
Yeah, yesterday in our discussion, we were lucky enough to have your colleague Drew and representatives from Structured Lamb and Perez, and now I'm gonna forget one, but Smart Lamb. Having everyone talk, you know, about the sort of the regionalism that they're producing in, and also the relationship between that material, you know, and the aesthetic. And I think, you know, as an architect, it's interesting to understand, you know, how you develop maybe an aesthetic language tied to regionalism and the material that's building, you know, these panels and these structural systems. You know, one thing that they brought up as well was that, you know, manufacturers are typically not the ones, you know, dealing with, you know, the architects or the engineers. I know your case, Lucas, you guys are pretty unique and successful in your model, but, you know, there was a discussion about envisioning sort of, you know, fabricators, right? So you guys would be sort of, you're already the secondary processors after the mills, but then is there, you know, a fabricator that comes online and they really negotiate with the designers or with the clients. And, you know, I don't know if you guys, you know, not to belabor the question, but we're sort of really interested, especially being down here in Miami. We do have, you know, a mill and fabricator in Dothan, but, you know, how do we sort of begin to build that network and disperse it and maintain some of those cost efficiencies and, you know, the construction ecologies that we're all acknowledging as a benefit to building with wood.
Well, I'll jump in first and just say that, I mean, I said maybe 8 or 9 times in my presentation that getting close to the manufacturer is the way to capitalize on real economy. But what I didn't say is that that's completely counter to a lot of the building design and construction culture of the US and the low bid, you know, the design bid build sort of design delivery process does throw up some barriers to that. We've been fortunate enough to be able to develop those kinds of networks and relationships with a bunch of different manufacturers and folks, and kind of understand where their sweet spots are and to be able to work in that. But it does take a certain amount of politicking and discussing with owners early on about what the delivery process should be. And if they, you know, basically say we can only work in a design bid build, you know, approach, well then ironically in my mind that means they're giving up on economy, which is what they think they're getting, because it doesn't really align. I feel strongly about that, so I'm pretty proud I was able to say that without cussing.
Hey, it's an open
I'm right
forum.
behind you, Greg.
You know, we put these panels together. We thought we might, you know, have the most sort of maybe tension yesterday when we had all the manufacturers together, but you guys can take this discussion whichever direction you want. No. Actually, I maybe selfishly, you know, as a practicing architect, but also as an educator, you know, there's a question here asking, how is the work in the Clemson engineering department transferring to the School of Architecture? Is there a good conduit between these two programs that have resulted in an educational impact between two programs? I think, you know, Peng, that's obviously directed towards you. Greg and Lucas, you're welcome to also talk, you know, about any of sort of the cross collaboration you're seeing sort of between engineering and architecture in your experience.
Oh, yes, certainly, you know, because as you introduced earlier, at Clemson, we have this wood utilization plus design institute. We put together the institute like 4 or 5 years ago. I can't remember exactly when we started. So, you know, in the institute, we have folks from different departments come together and work together. Even though we are in the same university, often, you know, we kind of work in the silo. So now we have pretty close collaboration between the forestry department and civil engineering and also architecture engineering as well. So for example, right now we are co-located in a lab. So we moved our lab recently, early this year before COVID hits, to a new lab space where architecture students, you know, they have their space, and then the CNC machine located next to our strong floor where we, you know, and also our actuator where we perform our testing. So the architecture student, I think it was last week, they have their studio class and they met at the lab. So my student kind of introduced to them, you know, their project. They were able to see the full-scale CLT diaphragm in our lab. And we also introduced to them, you know, how the CLT element put together, connection test, and so on. And several semesters, we use our civil engineering student as a kind of, you know, mock-up consultant for the architectural studio. So this semester, the architecture studio at Clemson, they are doing studio design, look into how to design building using, you know, mainly mass timber element to repair the Tyndall Air Force Base, which got damaged by hurricane. I believe it was Hurricane Michael several years ago. And, you know, the architecture studio student, you know, they design the form and all, and we have civil engineering students serving as a consultant to kind of give them some guideline. Hey, what kind of span length is possible, you know, and then the shear element and wall and so on. We provide kind of structural engineering consultation to them. Yes, there's a synergy between the two departments.
And Lucas, thanks. Dr. Ping, that was great. And I think if we don't start having those conversations, you know, at the education level where we're teaching our design students and our structural, you know, engineer students to think through wood and to understand a material language and to collaborate, then I would guess that projects, you know, at Lucas's level aren't possible. So maybe you could talk a little bit, Lucas, about some of that back and forth between the architect and the engineer, because the project that you shared, the freeform, you know, seems highly driven, you know, by the tectonics and by the engineering. So it almost like maybe you guys took a leading role, which is completely, you know, a possibility, but maybe not if you ask most architects. So I'd like to hear a little bit of that relationship.
Yeah, it's a great question. Actually, the overall form was totally driven by the architect in that project. And I mean, the actual final density of the grid and all that type of stuff was obviously driven by engineering. But the architectural concept was this kind of clamshell concept of having a dense grid at the back of the shells and a sparse grid at the front and minimizing solar gain just due to the sun path. So it was a very highly architecturally driven form and even pattern of the structure. But then, you know, it was a very close collaboration between the architects and ourselves to figure out what actual structural grid within those parameters would actually work. So very, very highly, you know, architecturally driven, but highly collaborative. We're involved in another project right now in Idaho for a basketball arena with office architecture. And again, you know, they came up with this beautiful, you know, form, doubly curved form from the Palouse in Idaho there. And so the form is driven by the architecture, but then how you kind of apply a structural system onto that form, I see that as like a really collaborative process between the structural engineer and the architect. It's almost like it's like a workshop. You know, it's like you're bouncing ideas off each other. You're throwing out things. Hey, can we do it this way? And you know, there's no one person who comes up with these ideas. It's got to be a collaborative process. And it's especially when you get into the more complex structures, it's all about collaboration between the design teams. And I like to think about, you know, moving back to the concept of the master builder or the idea of people like Eiffel and Brunel and many of these greats of prior times who didn't think of themselves as I'm an architect or I'm an engineer or I'm a builder or I only know about concrete. They just thought about building. They thought about building, and they thought about what is building, what is, you know, how close can we get to the edge of, you know, even look at the back of the Gothic cathedrals and how they kind of iterated to get to what the final form was by failing and then finally making it work. And so I think, you know, that process of a high level collaboration between the architect and the engineer is incredibly important to achieving good structural and good architectural design.
Yep, that's a great point. And the conversation that'll happen this afternoon, where we've invited some practitioners to discuss, you know, that's really how we want to engage, you know, what does it mean to work with wood in a material language versus, you know, maybe a specific product. And I think as this, you know, sort of mass timber agenda emerges throughout, you know, the US, of course, it's been around in other places longer, but a range of designers really start to engage it. I think engaging it through that lens in terms of pushing, you know, what a material can do versus, you know, applying products to a form, we'll really start to see some amazing things. I'm going to just read a comment that I think supports what we were just saying. Maybe I lost my train of thought. So sorry, I'm going to skip to one that goes back to the your specific project. So it said, I think it just went away. It was about the doubly curved. Sorry about that. Go back to it. How do you reduce the double curved GL? To be more specific, they are not curved, they are cut. So that was a question from the audience. I don't know if you want to quickly just sort of reiterate that process.
Okay, so I think the question is about on that particular dome structure, how we reduce the amount of doubly curved glulam. They are curved. All the beams are actually initially curved, singly curved, and then to achieve the double curvature in some of the beams where they did need double curvature, we actually CNC'd and cut out the double curve. So that means we completely eliminated the need to have initially doubly curved billets. We talked to the manufacturers who could make doubly curved glulam, and that would have been 2 full years of production, the volume on that project. Just completely untenable for the project schedules and even from a cost perspective. So we had to find a way to completely remove the requirement to actually press an initially doubly curved piece of glulam. So the way we did that is by changing, I would say 60% of the glulam into just singly curved pieces. And then the other 40% into double curved pieces that were doubly curved by actually cutting out the double curvature.
All right, well, we still have some questions in the queue, but we're sort of at the end of our timeline. So what we've been doing with the other panels is taking some of these questions, and maybe in the future in the next couple of days we can pose these to you guys, or we can bring them back in a later panel discussion. One of the comments that I want to read for you guys: all of the presentations today are fantastic. Thanks for answering my question. I think that construction across the landscape cannot even ask the question of what if mass timber without having a starting point. Is anyone aware of either software tools or consulting services becoming available or more available soon? And there's another comment in here that does say, as these design teams start to think, and to try to understand, how do we design a wood building versus designing a concrete building or a steel building, which, Greg, most of your presentation sort of focused on. Are these tools available that we could share with our audience, or how do you guys see them coming online in the future?
I will say, I can't say exactly when, but I know I'm certainly for our part, we're working with some partners right now to try to figure out how to get some of these automation and optimization tools automated and put online with easy access to architects to be able to manipulate plans and programs and so on with wood structures and find optimum systems relatively quickly. So it's not online yet, but we're working on it. So I would hope in the next couple of years, certainly you would see some pretty cool stuff available.
Right, and just maybe to follow up on that, I think what we're trying to do here is sort of produce a forum or a conversation that, poses those kinds of questions and that method of thinking. So I also think that the tools will be great, but also just to, engage any designers, both, architects and engineers that may be, in the space right now, just thinking differently and seeing the lens of how, you three specific presenters are thinking through wood as a material and some of the structures that you've been able to build. So with that, I want to thank all of you guys again for being present today. We've had, a series of great conversations so far, and I think your discussions today really took some of the questions that maybe were posed yesterday and answered them with a lot of detail. And we hope in the next conversations to take some of these practical applications like Lucas that you shared and sort of really expound on that, and also understand how does academics and teaching intersect with sort of this emerging methodology, if you will. So with that, I would like to invite everyone who's here. We're taking a short 30-minute lunch break, and we'll be back at 1:30 for our first discussion on track 3. So thank you, Dr. Pang, Lucas, and Greg.